Alright, welcome to my video playlist on similar figures and similarity. For this video, we're going to start with looking at defining what it means for figures to be similar. And then in the later videos of this playlist, we're going to look at using this definition to complete some example problems. Okay, so first we need to define what it means to be similar. Okay, in general, outside of like a math environment, when I think of similarity, I like to think of like siblings, like brothers or brothers and sisters, whatever. There's traits that you have in common, especially, specifically we're looking at blood relation here. So we're looking for maybe you have similar genetic characteristics because you have the same parents, but you are different people. Okay, you might even think of like fraternal twins where you share the same birthday and you have a lot in common with that person, but you're not identical. Okay, that's the key point here with similarity. We are not identical. We have shared common characteristics, but they're not exactly the same. Okay, so we would say that two figures are, we're going to fill in these blanks here, are similar if they have the same shape, but not necessarily the same size. Okay, so we're looking here and we're saying similar if we have the same shape, but not necessarily the same size. Okay, so looking at this example in green here, we have one shape that has the letters A, B, C, and D on it, and then we have another shape that's Q, R, S, T. So we can look and see that these two shapes are clearly different sizes, but as far as orientation goes, as far as the angles and the sides, we can look at these, and I am going to tell you that these are in fact similar the way that they were drawn. So we're going to name the first one A, B, C, D. So this is the four-sided figure A, B, C, D. And the second one is going to be Q, R, S, T. And for notating, we're going to say that these two figures are similar, which is going to be a single squiggle mark between them. Okay, so this symbol right here means is similar to. So the way that this statement would be written, or read, would be A, B, C, D is similar to Q, R, S, T. Okay, so that's some notation to go with this definition. Okay, so there's two characteristics that happen here when we have figures that are the same shape but not the same size. Okay, and the first of those is that corresponding angles are congruent. Congruent. There we go. Okay, and if we recall from our geometry vocab, congruent means same measure. Same measure. Okay, so corresponding angles have the same measure. Basically, what that means is that if, for example, like I see here on the screen, I have a figure with four corners, which are represented by angle measures, I need to be able to match all four of those corners up with a corner in the other shape that has the same measure. Okay, so starting with angle E, I can see that the measure of angle E, some notation there, M, and then this angle symbol E is the measure of angle E is equal to 135 degrees. That's also the same as the measure of angle W in the other figure. So then my first congruent statement could be that without the M, just angle E is congruent to angle W. Okay, so this symbol right here is congruent. Okay, stands for is congruent to. Okay, it's an equal sign with a squiggle on top. Okay, I have to be able to do this for all of the angles in my diagram. So I've matched up E and W. I need to be able to go and match up F, G, and H as well. Okay, so we're going to go ahead and write that out. And I can say that the measure of angle F is equal to 90 degrees. And that's also the same as the measure of angle X. So my second statement is going to be that angle F is congruent to, equal sign squiggle, angle X. Okay, the next one, I can see that the measure of angle G is equal to 90 degrees as well, which is also equal to the measure of angle Y. So my third congruency statement is going to be that angle G is congruent to angle Y. Okay, and lastly, I have the measure of angle H. That's going to equal 45 degrees, which is also congruent to the measure of angle Z. So my fourth similarity or congruency statement for the angles is going to be that the angle H is congruent to angle Z. And since I was able to show that all four angles in each of these figures matches up with an angle in the other figure, I have satisfied the first part of the definition of similarity. If I'm going to show that two figures are similar, I have to show that the corresponding angles are congruent. Writing these four statements out is what has satisfied that requirement for showing similarity. Okay? The second requirement is having to deal with the sides. And we can say that the corresponding sides are proportional. Proportional. Okay, we'll go ahead and highlight that too. Corresponding sides are proportional. That means that if I was to create fractions to represent the relationships from side to side, they should all be identical. Okay, so when we do this, the best thing that I can suggest is that we set up these fractions with all of the sides from one figure on the tops of all the fractions and all of the sides from the other figure on the bottoms of the fractions. I usually prefer to put the little numbers on top, so that's what I'm going to do here. I have four sides, so I need to set up four fractions. So I'm going to create four fractions. Okay. All right. And then a little trick hack would be to do all of the numbers in order from smallest to largest. So we're going to look first at the four side lengths that we have in the smaller figure. I have 5, 6, 4, and 11. I want to put those in order from smallest to greatest. So I'm going to start with 4, and then I'm going to put 5, and then I'm going to put 6, and then 11. Okay, and now I want to use the sides of the second figure. I want to use these four. Okay, so we're going to get 12 is going to be the smallest here, then 15, then 18, and last one is going to be 33. Okay, now what proportional means is that all of these fractions are equal to each other. Looking at them right now, they don't look like they're the same. But what I do recognize is that I can try to reduce all of these fractions and see if I can show that they're all identical. Okay, so if I use a calculator and I put in 4/12 into a calculator, I'm going to see that that reduces to 1/3. Okay, both 4 and 12 can be divided by 4, so we get 1/3. And then if I do the same thing with 5/15, that simplifies to the same number. So in my quest for showing that these sides are proportional, I've shown two sets of sides to be proportional. But because we have to show this for all of them, I have to do all four fractions. Okay, so in the calculator, we put 6 over 18, reduce that down. We also get another 1/3. And then for the last one, 11 over 33, that one is also going to simplify. So these are all the same, which means that the original fractions that we had are also all the same because all we did was simplify them to make the number smaller. That is satisfying showing that all of the sides are proportional. The second requirement for proving that two figures are in fact similar. Now, what's interesting is that when this happens and we get a common fraction for our proportions, this fraction actually represents the scale factor. The scale factor. So if we wanted to think of EFGH as the pre-image, and we are transforming it to make this image, we are scaling this by a factor of 3. So when we're looking at 1 over 3, we're looking at taking the first shape and scaling it up by a factor of 3. Okay? All right, and then lastly, if we wanted to write out the similarity statement would be EFGH is similar to one single squiggle, W, X, Y, Z. Now, when you are writing a similarity statement, you want to make sure that your letters are in the correct order. For the first one, it does not matter what order you put them in. Choose whatever you want. I like to choose to go around in a clockwise fashion, starting with the first letter that I see from the alphabet and just going in alphabetical order. Whatever method works for you. But it is important that we write it this way because this statement is going to tell us a lot of information about this shape without us ever actually having to see the shape. Okay, so I know from looking at this statement that angle E and W are corresponding, F and X are corresponding, G and Y are corresponding, H and Z are corresponding. I can also see that the side length EF corresponds to WX. That was the 6 and the 18, which we showed here in our fractions. And then we can keep going. We have FG, XY, GH, YZ, and then the first and last, EH and WZ. Okay, all of those fractions are right here from those side lengths. Okay, that is defining what it means to be similar and what we need to do to be able to show that two figures are in fact similar. Okay, go ahead and go to the next video for examples on how to use this similar figures property to work out problems. Good luck.